Good morning. The topic for this session is thin lens, as you see on the screen. And this particular topic follows previous topic, refraction through spherical surface. And even thin lens also, the basic is same as that of refraction through spherical surface. So we'll solve one particular question related to thin lens using basic approach of refraction through spherical surface. In a way, it's a revision of refraction through spherical surface. Let's take the example. The lens has two refracting surfaces. This one has a radius of 20 centimeter. Other surface has a radius of 30 centimeter and is made of material of refractive index 1.5. Let's take a case if object is placed at a distance of 50 centimeter, where would the image form? If we do not know about thin lens, how do we solve using refraction through spherical surface? So what would happen? So what we are talking about, if the image has to form through lens, it basically means that it need to be observed from other side. The observer has to be other side, and ray has to pass through the lens. It has to pass through the surface as well as this surface. It must undergo two refraction, one from this surface, air to glass, second refraction from glass to air. Let's do that. First refraction. In this case, we'll use the basic formula. What was our basic formula in case of refraction through spherical surface? It was mu2 by v. Let's look at that one. Mu2 by v minus v1 by u is equal to mu2 minus mu1 1 by r. That was the formula. Let's look at this. Where from the refraction, what is mu1 and what is mu2? Mu1 is the medium in which object is placed, which is air 1. From air to glass, mu2 is 1.5. And this is this is the pole here. Since this is the direction, ray will be traveling, object is on the left hand side, ray will be traveling towards right. So in the direction of motion of incident ray, this direction is positive, this being origin. So naturally u becomes equal to minus 50. And we put the values. How about value of r? The radius here, radius depends on position of the center of a spherical surface. For this particular surface, center is on the right hand side positive. Hence we write as plus 20. And when we put those values, we find V values is equal to 300. What does exactly this 300 mean? 300 means after the first refraction, all the rays which are refracted, all the rays, if we find the point of intersection of refracted ray, all the refracted ray will appear to be intersecting at a point which is 300 centimeter away from P1. That's what this point means. Okay, so and since and so this is how the refracted after first refraction is. Now the ray after first refraction becomes the incident ray for second refraction. So this becomes, so what was the object after first refraction? That becomes image for the second refraction. The image position becomes the object position for thin lens. Though for application of first formula, this was the origin, this was the pole. For second refraction, this surface, this is the pole here. So in a way, actually, there's slight shift in origin. But in case of thin lens, we assume the distance P1 and P2 is so small, we can assume that both are at the same point. So whatever value of image distance we had 300 centimeter, we can take the object distance also as 300 centimeter and object position also same as image position. So if now second refraction, again, we apply the same formula here. Now it is traveling from glass to air. Mu1 is that of a glass and mu2 is that of air. So 1.5 and this is 1. Same value of V goes as U here in this formula. And how about R here? Again, rays traveling towards right. This direction is positive. Center lies on the negative side. R is minus 30 as the radius of the surface is 30 centimeter. We calculate V comes equal to 600 by 30. What does this imply? It implies after refraction. Now, after refraction, it will the intersection point of all rays after second refraction would be at this point here. Okay, and just a small thing also we can add here. If we assume P1 and P2, this is not a thin lens. If lens thickness is T, what change would have happened? In that case, the P1, see the distance first image with form is at a distance of 300 from P1. A distance from P2 would not have been 300, it would have been 300 minus thickness. That's the only change. The U value, we have to take care of the thickness as well, which is very rare. Only very rarely we come across such question. So this is what we have done. We have solved as 2 refraction. And in this question, we have used actual number. If you use variables here rather than 20 centimeter, if I use something as R1 here, positive, and this also radius we assume as R2, and when we take this variable, we take it as positive, and we take U value, we take all variables, and in that case, what we arrive at, that becomes your thin length formula. And this is what the thin length formula is. 1 by V minus 1 by U is equal to mu minus 1 by R1, 1 minus R2. So this is what the formula is. We'll understand what this formula means, and this is called lens maker formula. So we can treat this whole thing as the length of this focal length. Okay, let's look at the next one. So if we use this one, we can find the value of focal length of this combination comes to 24 centimeter, and we substitute here, we find the value of B same as what here arrived here. Another important point what we notice here, see in this case, how was the lens placed? It suffered, see which surface was placed closer to the object? The surface having radius of 20 centimeter. If we flip the lens, what does flipping the lens mean? If we flip the lens, now which surface is facing the object now? Not 20 centimeter, 30 centimeter. So in this case, if we flip the lens, keeping the object distance same, will the image distance change? Actually, it will not change. We can also understand in terms of formula. So basically, again, we'll see later how do we use that part. This term still comes out same. Focal length remains same. So it is independent of which orientation we place the lens, or whatever focal length we have. If the rays are traveling in this direction, in other direction also, if you reverse, object is placed here, image is forming here, even then the focal length remains same. Only condition is, see what we have assumed here, we have assumed this to be air, this to be air, and this to be mu here. So we have assumed lens is placed in the same medium. So as long as it is placed in the same medium exists on either side, in that case, focal length is independent of direction. If there are two different mediums, that's a complex case. That case, it will not be same. Let's understand how to find effective focal length of the lens depending on different shapes. So lens can have various shapes, and biconvex, equiconvex. Equiconvex, both are equal radius. Biconvex, all these things are there. What is important to understand, first getting this sign convention. So there are two surfaces here, and typically if this is the direction in which the rays are coming, based on this direction being positive, if we have to assign the sign, the R1 and R2 values, the sign depends on where does the center lie. This would lie on the right hand side, this will be positive and this will be negative. Hence when I substitute, it will be equal to 1 by R1 minus of 1 by minus R2. It will add up. It will become, whole thing become, both term will become positive. Similar way, this also is positive and this is negative. Both terms will become net positive. And in this case, of course, this is infinity and the second one is negative. This one is negative. So here also, if I have to apply this formula, if you have to calculate this term here, it would be first one, 1 divided by infinity, and minus of second term, minus of minus r here. So again, this term becomes positive. So this also net positive, this also positive, this also positive. Similar way, if you look at this, this is positive, this is positive, this is positive, and this is positive. But in this case, what we notice here, see radius of curvature R1 is smaller than R2. So if I evaluate this term 1 by R1 minus 1 by R2, I write this R1 as positive, minus 1 by R2 is positive. You notice here, this curvature, this seems to be part of a bigger spherical surface, R2. So if R2 is larger, the negative term is smaller than positive term, whole term will come as positive. So see what we noticed so far, all these terms were, all this come into the group where this term evaluate to positive. And if it is placed in air, this term also is positive, focal length will come positive. So these all four are what you may call as convex lens. Okay, these are all convex lens. And these four, so how do we define convex lens? And let's understand it. There are two ways to understand convex lens. One in terms of mathematical expression. If we evaluate this term is based on the geometry of lens. Basically, radius or curvature of two surfaces they are part of. If this terms evaluate positive, it's called convex lens. And second thing, intuitively, we look at if the middle part of the lens is thicker, then it is called a convex lens. Here also notice thicker, thicker, thicker. Even this place also is this narrow, this is thicker. So if this is thicker, it is a convex lens. But in terms of behavior of lens, a more appropriate one we distinguish as convex and concave. This is convex category, and other are concave category. How do you understand? Yes, this term will evaluate positive, this term will evaluate negative. Other better term perhaps is converging lens. And converging lens itself, the word converging, this gives you better understanding of behavior. It tends to bend the refracted rays towards principal axis. Okay, so if it is a converging lens, if any ray comes like this, if you take this example of this lens, this was the original direction, it will always bend it towards principal axis. This way it will bend, not other way around. Whereas if I take a similar ray in case of diverging lens here, if this is original direction, it will bend it away from principal axis. So converging lens tend to bend the refracted ray towards principal axis. And for that, this whole term need to be positive. Okay, so what makes this term positive? One, both are positive. What makes both are positive, this term as well as this term? This term depends on the geometry, and this term here we see this depends on the medium in which it is placed. So if it is placed in air, yes, of course, this will always be positive. So any lens which is placed in air, it is a converging lens if it is a convex lens. Or more general way, if lens is placed in a medium which has refractive index lower than the lens material, so all convex lens will be converging lens. So both term positive. This whole term has to be positive. That's a converging lens behavior. And converging lens behavior is very similar to concave mirror. What we mean by similar behavior? A concave mirror and converging mirror, if both of them have same focal length. So this is how we calculate focal length of a lens. And in case of concave mirror, focal length is equal to r by 2 and is of negative sign. So if we have a lens and a concave mirror, both have same numerical value of focal length, then for same object position, they will form identical image. Only the sign of V is different. So what we mean by identical image? So if we have if both have same numerical value of focal length, whatever is object size, if image is formed for given object position, if image formed is real, inverted, and magnified by concave mirror, even converging lens also will form a similar image. Let's understand in this case and try to relate to concave mirror. See here also what we have done in case of the term C actually is relevant only in case of mirrors, because the surface has a center here. There are two surfaces here. The C is not meaningful, but just to compare with the mirror, I have written C here. C implies actually 2f distance, and we can mark on either side also, as we see. Now, image nature in case of concave mirror as well as convex lens depends on object position. And how do we typically distinguish object position? These are three regions. One region, if object is moved from infinity to 2f. So basically we say if object is placed at a distance greater than 2f. How is the image formed in case of concave mirror? Image was real, inverted, and diminished. An image used to form between focal length and this region where in case of concave mirror, image used to form. Everything will be same here. Only thing what will happen, since this was the real space in case of concave mirror, real image, here real image is here. So here at infinity, image will form at the focal length. As the object moves from infinity to 2f, image also will move for this corresponding position. Where is the image for this corresponding position? This is the image. Image will be from focal length to 2f. So when object is placed at 2f, image also forms at 2f. Similar way, if we continue, if we take the next example, next one, Next range is if object distance is between f and 2f. In that case, image will form between 2f and infinity. The corresponding here. Now, what is the image distance? Between 2f and infinity, it will move from 2f to infinity. And what will the near? Both cases. Here also, both cases, image is real and inverted. Only thing here, it was diminished for this position. Now here it will be enlarged. And very similar to, and if third case we take, what is the third case? When the distance of object is less than focal distance. If this is where the object is placed. If it is placed in, what kind of image used to form in concave mirror? Virtual image. Here also it will form virtual image. So let's try understand virtual image is what? Which is the virtual space for a lens. This is the left hand side is the virtual space. So if focal distance, this image will form something somewhere here. So image, so what we notice similar to concave mirror, maximum magnification is produced near when the object is placed close to the focal distance. If it is slightly more than the focal distance, real inverted enlarged image will form at a long distance at positive infinity. If object distance is just less than the focal distance, then erect, virtual, and enlarged image will form at minus infinity. So this is where maximum magnification happens, and this point is useful in case of basically we see later microscope and magnifying glass. Okay, so just more than focal distance, real, and just less than focal distance, virtual image in enlarged. Okay, now let's understand what happens. Why, if entire lens it has some refractive index mu, if it is placed in a medium which has a refractive index mu m is greater than mu of the lens. See, typically we expect the whole behavior should change, and very easy reason to understand what would happen in case of refraction. Refraction, the ray bends. If it moves from rarer, if when it moves from medium to lens material. If lens material mu is higher, the ray would have bent towards normal. But if medium refractive index is higher, the ray will bend away from the normal. So both case direction changes. So one case was bending towards normal. Now, if this is high refractive index, it will be bent away. And that changes the behavior. So if medium has a mu greater than that, how do we account for this? Formula is very similar. Let's look at that. Only change we make if there's a different material. In case of mu, we use a relative refractive index. And what does relative means with reference to what? This is refractive index of the less material with respect to the medium. Mu r is equal to mu l by mu m. And if mu m is greater than mu l, this term becomes less than 1. So this whole term here becomes negative. So even in case of this, if this term is positive, as in case of convex lens, if this term negatives, whole f becomes negative, it becomes a diverging lens. So if a lens is placed in a medium which has higher refractive index than the lens material itself, its basic nature changes. Converging lens becomes diverging lens, and diverging lens becomes converging lens, because this sign becomes negative and this sign changes the sign of f. So again to come back to the formula here, f depends on two things here: geometry of the lens as well as the medium and the surrounding medium, refractive index of the lens as well as the medium, right? Now we talk about power of a lens. And those who use reading glasses or whatever, they understand the power. Okay, power is termed very often. Every time you go to optician, they will tell you you need this kind of power. What does power mean? Power is equal to inverse of focal length, and the focal length should be written in meters. That many diopter is the power of the lens. And if f is positive, if it is converging lens, power is positive. If it is diverging lens, power is negative. What happens in case of combination? If you have combination of lens, yeah, something like this. Here also two lenses kept side by side, two thin lenses, two lenses kept side by side, even three also. In case of combination, we can treat them as one lens of having equivalent focal length given by this expression. So, or in terms of power, it is much easier. If two lenses are there, if the ray has to pass through both the lenses, effective power is sum of the power, which makes very intuitive sense. In this case also, image formed by the first lens becomes the object for the second lens. And okay, so now when we look at the lens, what you notice from here, there are a number of ways hypothetically a lens can be cut. So in this particular case, when you look at this, we use certain thing called aperture. What is the aperture of the lens? This lens would be cross section. This is something, the diameter of the lens is the diameter of the lens, not the surface diameter. Okay, the diameter of the lens is called aperture. It gives the size of the lens. So here, if we cut the lens in two parts, okay, suppose this radius is R1 and this radius is R2. And if we cut into two parts and two parts are placed like this. So earlier the focal length was E. What would be the focal length of this combination? This is something, it is placed like this, it is placed other way around. So how would F1 and F2 be? Actually pretty simple. All three cases F1, all three will have same focal length and it's very easy to arrive at. So okay, so in this case also you have to look at what will the focal length. It will be focal length of this plus inverse of focal length plus this plus this. So if I write what will be F1 by F1 will be, it will again be equal to mu minus 1. See, what was the focal length here? This focal length also 1 by F was equal to mu minus 1. And since you know we have seen earlier R1 positive, R2 negative, it was equal to 1 by R1 plus 1 by R2, negative, negative. Similarly, if I calculate this one will be equal to mu minus 1, 1 by R1. And the second one also, if you like one, it will be equal to mu minus 1 into 1 by R2. Sum of these two, 1 by F1 plus 1 by F2. Basically, again, you find this and this are same. And this way also, what will happen? This also will come same. What has happened? It has been flipped. And we know when we flip the lens also, its power does not change. All three will have the same power. Now, if the lens is cut in this fashion, before we understand, we can just look at one more way. See, when we have a lens, just try to think of this. This is a lens material. Typically, lens is made of only one material, which has same value of mu. Let's assume a case here, the lens is made in a very funky way. The different parts of the lens are made of different material. Okay, and if it was only in one material, so basically what will happen here? So each part here, if all were made of one material, what happens when we place an object? All of them, suppose if it is placed on one material, all of them after passing through the image for a given object distance, each part of the lens forms image at the same point. So in a way saying, if we treat different part of the lenses also, each part of lens will have same focal length if mu value was same. So each part of the lens behaves like independent lens of same f. So if we remove rest of it, we remain only this part also, it will have same focal length as the rest. But if they are made of different material, so you see a light gray material, dark gray material. If this focal, if they are made of the same material, this, and this will have same focal length. It means if I place an object here, the gray line which is passing through this material, if one line from here comes and intersects here, so this is one ray, and second ray we can always take passing through, this will go undeviated. This is where for this object, this is where the image is getting formed by this part of the lens. Even this part of the lens also, as long as curvatures are similar, mu is same, even this also, the ray which will bend will go like this. So even this also will have same focal length. Whereas if we take the different material, the darker shade, which has refractive index mu2. If mu is different, even though radiuses are same, its focal length will be different. If focal length is different for same value of u, v will be different. It means image position will be different. So if I draw refracted ray, assume that it goes like this. So here, in this case, image is forming at a larger distance. Actually, this image is forming a larger distance. It means it is bending it less. The power of dark gray part is lower compared to light gray part. That's why the bending is much less compared to other one. Since the bending is less, image is forming at a larger distance. And why is value power is smaller here? The power is something like what? Power is 1 by f. Power is depends on, yeah, power is something like this, mu minus 1, 1 by R1 minus 1 by R2. So here, both of them have same geometry. This part is not different. If power is less, is only because of mu. So here, if a diagram is given like this, what can we conclude? We can conclude that mu2 is lesser than mu1. So if their lens is made of two different refractive index, it means it will form two images. If there are three such material, it will form three images. Let's come to cutting again. Again, this figure here. Suppose lens is like this, earlier a cut like this. What happens if I cut like this and place two parts like this? There are two lenses now. If we cut also, this shape has not changed, mu has not changed. As we discussed with each part, this also, if this had a focal length f, this piece also will have, and this also will have. If we place them side by side, if we assume them thin lens and distance to be negligible, this combination will have a effective focal length of f by 2. So focal length becomes half, power becomes double. Okay. Coming to some more question of combination of lenses. See something like this, liquid or refractive index. Assume that you have two concave lens, biconcave lens, and there's space between the two. Actually, you're seeing in two dimension, this will form a kind of cylinder with two surfaces inclined. This is like a cylinder, this is also a cylinder, and this empty space. And if we seal this space, we can fill up a liquid and seal it up. So it is like this, glass, liquid. So, and what are the mu value is given? Mu value of liquid is given as 1.6. And mu value of glass is given as 1.5. And radius of each curvature, all this, with this curvature, this curvature, this curvature, all are 20 centimeter or 0.2 meter. What kind of lens it will behave as, and what would be the focal length? How would you calculate? It's a combination of lenses. So here, what we notice, sometimes we get confused here. This side is air, this lens is glass, other side is liquid. So what should we take here? So whenever it is two different kind of medium, they're placed like this, we can always imagine there is a very thin layer of air in between, and like this. And if there's a thin layer of air in between of both the surfaces of air, will have same radius as the radius of curvature of this boundary between the two. So this also will have same radius, this also will have same radius. So effectively what happens, moment we imagine an air in between, then it becomes like this. This lens also is placed in the air medium, this lens also placed in the air medium, this lens also placed in the air medium. Or if it is water here, we can imagine a thin layer of water. And since two values radiuses are equal, it does not deviate the path. So it does not affect anything. It only helps in conceptually simplifying the problem. So whenever different medium also, we can ignore, we can assume as if all three lenses are placed in the same medium as the surrounding medium. Let's say, now imagine gap, we have done the imagination. Now, if we have to calculate the three lenses, these two lenses have equal power. Let's calculate the power of one lens by concave lens. So power is equal to mu minus 1. This is a formula here. And in this case, yeah, this will be R1 will be, if this radius is, yeah, R1 is negative, R2 is positive, both term will come out negative. And since all are equal, it becomes minus 2 by R. This whole expression will evaluate to minus 2 by R. So minus 2 mu minus 1 by R. We substitute value of mu as 1.5, 1.5 minus 1.5 into 2. Yeah, this expression. So we get P1 here, R is equal to 0.2. Since we are talking power, we are substituted in meters. So this will have a power of minus 5 diopter. What does negative sign indicate here? Negative sign indicate is a diverging lens. Now, liquid part is like convex lens. R1, R2, both radiuses are same. And in this case, both will see second one is, first one is positive, second is negative. Both will again become additive. It becomes 2 by R. Here it was minus 2 by R. It becomes 2 by R. Mu minus 1, we put this value, mu is equal to 1.6. This expression P2 we get here. What is the combination? Power, effective power or equivalent power is twice P1 plus P2. So we put those values here. We find, so value of inverse of the power, F value comes equal to minus 0.25 meter. Minus indicates the whole combination will act as a diverging lens. So saying here whether it's convex lens and concave lens, that is meaningless. Perhaps a more effective way, more appropriate is behavior. It's a diverging lens. Okay, next look at the, okay, what is given here? Again, is combination of two thin lenses. So one is plus 20 centimeter. The plus for first one is a converging lens. Second one is a diverging lens. They form, if combination lens, respectively form an image of distant object at 60 centimeter. What does it mean? If a parallel rays are coming, okay, that means distant object, infinite distance. It will get reflected from here, it will get reflected from here. Basically, say the final image after two refraction forms at a distance of 60 centimeter. Okay, so this way, so after two refraction, this rays which are refracted rays will appear like this. And the intersection point, they will actually intersect, so will form a real image. Okay, that's what is given here. And actually, if you look at this, yeah, so we could have, even this also was not necessary, we could have easily calculated. If since both the focal lengths are given, we can calculate equivalent focal length, 1 by e square 1 by f1 plus 1 by f2. That would be equal to 1 by v, because 1 by u term will be equal to 0, and which comes equal to 60. So that is tells you another way to define focus. What is focus? Focus is the point where image forms when object is placed at infinity. That's focal point. Right. Now, what is the second part here? What will be the position of image when two lenses are placed at a separation of 10 centimeter? How are those two lenses placed? First, it is refracted through converging lens, then it is refracted through diverging lens. Let's do that part here. So first image here, we can easily find where, since the incident ray are parallel on the first lens, image will form at the focal distance, which is equal to 20 centimeter. V1 is equal to 20 centimeter. Why we are written a V1? V1 is an intermediate image. One more refraction will take place. So this is, if we visualize the figure, this is how the figure would be. And how are all the distances calculated here? All the distances, since we are talking about refraction first lens, this would be by coordinate system. With reference to this coordinate system, origin being at the optical center, these are the values. Now what we need to do, this, these refracted rays are incident on the second lens. So these rays become object for the converging, for the diverging lens here. Okay, so so what is the object, what is the value of u for the second lens? To use the formula for second lens, I need to find the value of object distance. Where from we'll measure the object distance? We'll measure the object distance not from here. We need to measure the object distance from its optical center. This becomes like, so it is like we are shifting the origin. Earlier, this value of v1 was obtained with reference to this point. Now, for object so object distance or object position will be measured from here. That would be equal to whatever value of, see, if I write in general terms, we know whenever we shift axis like this, x dash will be equal to x minus the distance d. So similar way, you have to write, it will always be v1 minus d, and v1 is equal to here f1 minus d, 10 centimeter, and it will be virtual object. And virtual object, so once we know the value of u is plus 10 centimeter, we substitute here, we find v is equal to 15. Let's understand, even otherwise also, this was, see, this was where the object position was, and this is a diverging lens. So the ray which is coming like this was the original path. Which way will the ray bend? If it bends like this, it will be converging. If it bends little away from the principal axis, that becomes diverging. So this is perhaps how the rays will go, and that's why the image gets formed at 15 centimeter. It moves further away from here. Okay, next question is again about a change in behavior of a lens when surrounding medium is changed. So there's a thin converging lens of power is given 5, and this is the medium refractive index. Okay, so what does this mean here? We know power. Okay, and when this lens is immersed in a liquid of refractive index, what are we doing here? We are changing the medium. So this is how the power of 1 by f of a lens is mu r minus 1, 1 by r1 minus 1 by r2. So whenever we change, we submerge into some other medium, the geometry of lens is not changing. This term is not changing. Which term is changing? Only this term is changing. So what will happen? So we understand here, power is proportional to mu r minus 1. So what are the two powers here depending on the medium? So when it was in air, what is the power in air initial? P1 was in air. That would be equal to mu minus 1, mu g minus 1. Because and when it is placed in the liquid, that is P2. P2 in the liquid will be equal to what? That will be mu r. What would mu r be? Mu of the lens divided by mu of the liquid minus 1. Let's put those values here. Ratio. So what is P2 by P1? P2 is equal to, 1 meter and its divergent, that's why minus 1. Its power is minus 1 diopter. This is 5. And that would be equal to mu r corresponding to P2, which is mu g by UL minus 1. And mu r minus 1 corresponding to P1, which is mu g only minus 1. So we know value of mu g 1.5. We can easily obtain mu l. Value simplify. We get mu l is equal to 5 by 3. And 5 by 3 is greater than 3 by 2. Is that significant? Yes. Since reason the nature of lens has changed because it has been placed in a medium which had higher refractive index. Of course, this whatever if the nature has changed, this term has to be greater than 1.5, and it is greater than 1.5. So then only if medium refractive index is greater than lens's material's refractive index, then only the nature of lens changes. Okay, another interesting one. So what we see here, this is a pretty neat looking figure. What this figure indicate here? Assume this is a kind of a cylinder made of a glass. A glass is a cylinder of a small length. Okay. Within this glass cylinder, we scoop out. Yeah, we are used to cavity. Sometimes cavities are very commonly created. So cavity has been created and which creates air gap here. And the cavity is form of two surfaces. Each surface has certain radius. This surface also radius is 10 centimeter. This also is 10 centimeter. So this is what we are left with. So if we have this kind of material cut in a cylinder of glass, whatever is given, so this is this perfect. Again, if the light cup falls onto this, it will behave like a lens. It will bend the light. So can we find out what would be the focal length and nature of the lens? Yeah, let's do that. Let's understand how are we going to do it. See, in this case also, if we pay attention, if both radius are equal, I can see two lenses. One part left half and right half, both are similar to each other. So it are two lenses of equal power placed next to each other. What kind of lenses? This is also diverging lens. This is also diverging lens. Both will have equal power. So can we calculate equivalent to convex lens, concave lens? Okay. So let's write those terms here. What would be the power of one of the two lenses? Power will equal to mu minus 1. So okay, both sides air here. So mu minus 1, 1.5. So this is air itself. So mu itself will come. And what would be, okay, so if I have to write this 1 by R1, 1 by R1 is 0 because R1 is infinity. So minus 1 by R2. R2 is positive. That's why overall this term comes negative, which makes sense. Anyway, all time this has to come negative. So this power of one lens, power of two lens will be twice of this. And from there, we can get the focal length, which comes to minus 10 centimeter, which is diameter. This is another case here, similar to previous case was a cavity created in a glass cylinder. Here we can think of, we can from thin polythene sheet, thin polythene transparent sheet is in form of a cylinder. And within the thin polythene sheet, this thin polythene sheet only holds the material. Its thickness is so negligible, it doesn't affect the refraction process and all. So it is like a thin shell or thin plastic sheet, which forms a casing kind of thing. And this casing contains, what is it? It contains a lens of focal length 20 centimeter. So it contains a lens and remaining space is filled up with the liquid. So only difference what we noticed there, it was a cavity had air, here the cavity had glass. So something similar otherwise. Can we also find out focal length of the system? This is also similar. And three lenses here. And whenever three lenses are there, we always assume there's a small layer of equal radius on other side between two lenses. So there are three lenses. And again, we can easily calculate for lens placed in air. We can easily calculate this value. So what we do here, first we start with the lens here. See what is missing in this case, R is not given. What is it? So first to find the focal length of this plano concave lens, we need the radius of surface here. And since focal length of the lens is given, is refractive index given, R can be found from lens formula of this particular converging lens. Let's do that. 1 by f will be equal to 2 mu minus 1 by r. So we get the value of 1 by r is equal to 20 centimeter. Once we have the radius, we can find the left part of the concave mirror, the concave lens. Again, we can mu minus 1 minus 1 by r. So this becomes a power of first part. Second part also same, and total power will be this multiplied by 2 multiplied by this. That becomes the focal length. So combination of P becomes minus 1 by 100. This is 1 by Fe. If this is 1 by Fe, focal length is equal to 1 meter, negative 1, and it will, since it is negative, it will act as a diverging lens. Now we come to one more experimental kind of experiment what we have related to lens. And this experiment is called displacement method. This is used for finding focal length of convex lens alone. And in case of convex lens, this minimum distance between object and real image is equal to 4f. When we place an object at a distance of 2f, image forms at a distance of 2f. As we move the object from 2f, the velocity of image is greater than velocity of object, or distance moved by image is greater than distance moved by the object, hence the distance increases. So minimum distance 4f. So here, what is the experimental setup? We have an object and we have a screen. Both of them are placed at a fixed distance d, which can be measured. Okay, and then we have optical bench here. This is something for short. And we, from here, we start moving the lens towards right. So basically what are we doing? Slowly we are increasing the object distance. So at particular value of object distance, I'm using the word distance only. At particular distance from here, I find a sharp image on the screen. Okay, and so this is the distance here. And then if we continue, so there's one particular position. What we find here, again, if we continue, if I move the lens further by a distance x, or from first position of sharp image, if I displace the lens by distance x, I find another sharp image. And this is a displacement of lens. That's why I call it displacement method. There are two different positions of lens for which a sharp image is obtained without changing the distance between object and the screen. And very naturally, and this makes very easy sense in terms of formula also, what is happening, why this is happening. So if first one was, this was u, and this particular value will be v, this v will be equal to d minus u, of course. So when u image forms at v, if the object distance become v, image will form at u. Those distances are interchanging. Okay, so image distance. So now when we find focal length in terms of in terms of experiment, we record two values. We record d distance and we record x distance. So based on these two, we can find out focal length. How do we find out focal length? Let's understand here. So in this case, okay, what is x equal to? X equal to v minus u. That's x equal to. And what is d equal to? V plus u. So I can find, both are distances. U and v are distances. The distance v will be equal to d plus x by 2. Distance u will be equal to d minus x by 2. Now I can substitute in less formula for the first case. 1 by v with sign, this is positive sign, distance positive, minus 1 by u, but u will be negative here. This is what per real object, a negative sign. So when I substitute, I simplify, I find focal length comes equal to d square minus x square by 4d. And another thing I come to across here, let's see if the object height is h naught here. Okay. First case, what would be magnification? Magnification first case will be equal to minus v by u. First case magnification is minus v by u. So what will be the image size here? Image size will be equal to minus m1 into, sorry, m1 into h naught. That's the image size. And second case, the I2 will be equal to m2 into h naught. But what is m1 and what is m2? See, we will very easily notice m1 is equal to minus v by u and m2 is equal to minus u by v. They are inverse of each other. So if I multiply these two, what would I1 into I2 be? If I1 into I2, height of the image, first image, into height of second image, will be equal to m1 into m2 into height of object of square. This term is inverse of each other is 1. So it tells you object heights. If I measure the image height, the geometric mean of image height will be object height. And those two magnifications are inverse of each other. And in terms of solving question is fairly easy. Let's look at one numerical. Distance between object and screen. This is from previous one. If you look at D is given and X is given. If D and X are given, from here very easily we can figure out. See, this in this case it has moved about midpoint. So this distance X is 40 centimeter, and you will be very easily you can find out clearly that U will be equal to 30 centimeter and this will be equal to 70 centimeter. This difference is equal to 40. That's why the displacement also is 40. So U and V, the difference is 40. Once I have these two values, I figured out 30 and 70. Now there is nothing else is required. We can U is equal to minus 30, V is equal to 70. I can find focal length, I can find magnification, everything can be found. It's simple. Okay, let's look at some question where lenses are not close to each other. I cannot use equivalent focal length. I cannot take take the sum of the power. So what is given? Object is placed at 12 centimeter and both the focal lengths are given 8 centimeter, 6 centimeter. Both are converging lengths. Okay. So question what we need to find, the distance between them, all these things are given, object distance, distance between two lenses. What we need to find, what will be the image formed by the second lens. Of course, image will form only when it is passing through both the lenses. It will have a particular field of view. The rays have to reach here, observer here to somewhere in this side, then only those image will be seen. Let's solve very simple. We'll calculate one lens at a time. Only thing what we'll keep mind, my approach is going to be pretty simple. Image formed by the first lens becomes the object for the second lens. That's all, nothing else. Let's do that. Two lenses are given. If this happens, it could be two lenses, it could be one lens and one mirror, it could be two mirror. All cases where two are involved, when reflection or refraction are taking through both and then final image is forming, image of the first becomes the object for the second. Only thing we need to take care of the object image position because their optical centers are not same. I cannot substitute directly. So if I call object distance as U1, image form is V1. If this object distance is U2 and final image is V2, U1, U2 is not equal to V1. U2 is equal to V1 only when the optical centers are very close to each other. They are not equal. That's what we'll understand here. Let's understand. If the distance is D here, if this distance is D, then very easily we'll notice here, we see that in this example also, if the distance is D, U2 will always be equal to V1 minus D. Let's see that one. Because X is shifted by distance D. Let's see, let's solve this concept. There's two cases. First case, this is the origin here. First case, a simple substitution lens formula. I find V1 is equal to 24 centimeter. What does it mean? This object is placed here. Of course, where do you find this object? It's 12 centimeter. So 12 centimeter object is between F and 2F. This is between F and 2F. F and 2F, it will form real, inverted and magnified image. It forms image which is twice as much distance. So if this height was H0, this height will be equal to 2H0 and will be inverted image. Okay, this image it is formed. Now you can always forget the whole thing. Now, as far as the second lens is concerned, this is the image. And this same principle we follow in case of optical instrument. So this becomes image. I forget rest part. This is where the image is. Now, only problem is I know this distance is 33. This distance is 24. As far as this lens is concerned, this is my coordinate system. I need to measure the distance from this optical center. And what will that distance be? As I said, it will be equal to axis is shifted towards right. So x dash coordinate in that system will be x minus the distance between two coordinate system, two axes, translation of axis. So 24 minus 33 minus 9 centimeter, which from figure we can notice. If we had drawn the figure, we notice this minus 9 centimeter. Again, we substitute, we find V2 is equal to 80. And here also pretty simple. If it is 9 centimeter, again the object distance is between F and 2F. Again the image will be inverted, magnified, and real. That's how the image will form. And as the okay, so from here, if I look at that, if I look at the ray, if I have to draw the ray which goes from the optical center, goes like this. And from similar triangle, we can find magnification. Here also we can find magnification. Similar triangle twice as much. Okay. So first image real inverted magnified. So what we notice here, this also inverted, and this is inversion of inversion. That's why it becomes erect. Real erect magnified image gets formed. And if we have to calculate what is the resultant magnification because of two lenses put together, resultant magnification is m1 into m2, which is 4, and which we can easily understand from the figure also. It is 4 times the object. Last question, convex lens A of focal length of 20 centimeter. This is minus 5 centimeter. Minus 5 indicates it's a diverging lens. They're kept on the same axis. Distance between them is d. A parallel beam of light falls on A. So what is the object? Is that object is at infinity. Okay, so this would have formed image at its focal distance. It would have formed image at 20 centimeter. Right, so falling on A. In between something, what we need to, what is the value of distance d such that after passing through B, again the rays are parallel. What has to be value of d so that the final image also, the emergent ray are parallel, or you can say the u is infinity, and the final image also gets formed also is at infinity. We can solve this question in two directions. What is something we start from here and solve, and second thing, we start from the final image and corresponding work back and solve. Either we can solve, okay, object position. So we can, if we work back, if I look at this lens alone, so if we have a diverging lens, what should be, where should the object be so that image forms at infinity? Can we work it out? Okay, so let's look at the formula also. So if I look from this angle, where should the object be so that image forms at infinity? Let's look at it. What is the formula? 1 by v minus 1 by u is equal to 1 by f. So basically, if I want this to be infinity, minus 1 by u has to be equal to minus 1 by f. F is negative here. So at what distance u, what has to be u value? U is equal to f. So, and if I visualize here, if this is 5 centimeter, what should be the nature of incident ray? This is how the incident ray should be. Something like this. And this incident ray should form a virtual object at its focal. Then only it becomes like this. And you notice here, these rays which are coming here, again it is moved away from the principal axis. So which basically means this is where the object is needed for the lens. And this object, who will form this object here? Where from the object will come? This object is nothing but the image. So this lens should form an image which is 5 centimeter in front of the diverging lens. And but we know this lens forms an image at a distance of, what distance it forms? Focal length is 20 centimeter. It forms an image at a distance of 20 centimeter. So rays which are refracted from here, they appear to be intersecting at a distance of 20 centimeter. So what has to be the d? If this is 20 centimeter, this has to be 5 centimeter. D has to be 15 centimeter. So image by first is 20 centimeter. Object distance is 20 minus d. That has to be 5. So the d has to be 15 centimeter. Right. So that brings to end of lens. And next session we'll take up silvering of lens.